All right, we'll talk about transition states and also intermediate states. So what are these? So we'll get to know the definitions, the rules used in these guys or in studying these guys. We'll also talk about just some stabilities, including the energy diagram itself. All right. So without even wasting our time, let's start. So this covers industrial chemistry, pure chemistry, pure biology, education chemistry. This is just organic chemistry in general. So you are covered. So hope everyone is there in the meeting today. All right. Okay, I will post the video. Yes, you can even invite your friends. You will even share to your friends. All right, because it will be very helpful in your test ones and even just session. All right. So what we need to know is that transition states and intermediates, they are both short-lived molecule formed as the reactant are turning into what? Into products. So transition states, both the transition state and intermediate state, are short-lived molecules formed between reactants turning into products. So those are the what we call transition states and also intermediate states. So would depend, I mean the stability would depends on where they can do what. For example, let me give you the reaction. So for example, so the first thing that I've given you is to say they are both short-lived molecules. So these are what? These are short-lived molecule formed, all right. So these are short-lived molecules, all right. So they are formed between all right. So they are formed between reactant turning into products, all right. Into products, all right. So those are will be in between. If we can recall, we can get this a best scenario. It is in the state, in the situation whereby you have what? Ionic equation. So those spectator ions, they will cancel, right? Those we can call them intermediates. All right, they are just intermediate, like they are in between the reaction turning into product, but you won't see them at the end. So okay, for example, let me give you a general mechanism of a reaction. Okay, let me give a general mechanism of a reaction. A reaction, let's say, that involve what? Let's say I have chlorine, all right, chlorine plus hydrogen turning into what? 2 chlorine hydro, or just the hydrochloric acid. All right, so now what I'm going to do is I will say this reaction will involve some steps, all right. That's what we call series of steps. So what we are going to do is I'll say the first thing I'll do what? I'll bring this reactant here, the bond the way it is, okay. Then it what? It will undergo breaking, or we just break this one, okay, plus that, okay. So from there, now step 2 will say we're going to bring one chlorine there plus this hydrogen we have, all right. So the bond that of those hydrogen then turning into what? Will attach these hydrogens to this carbon, so I mean this chlorine. So this will be what? Like this, okay. So this is partial thing whereby we can't have a situation whereby chloride 2, something like that. That can't happen. So I'll definitely circle this one to be one of my what? My intermediate. So it can be intermediate or what? Or just a transition state. So let's call the step 2. Now I'll have what? I'll have the same thing here, chlorine bonded to hydrogen, another hydrogen there, okay. Then this is now turning into what? We are leaving one hydrogen, okay, then plus another hydrogen like that. So still we have again another thing which has just been formed. It was just there to help the reaction finish or complete. Alright, so that's another transition state or just the intermediate state. I don't know, it will depend on the stability. Okay, then the other thing that I can do, the last step now to finish or to complete this reaction that I've just made for myself, I'll say I'll bring now C H plus, alright, hydrogen is equal to what? I mean giving us chloride hydrogen like that. Alright, so we can see this one we can see this is a transition or intermediate state, is still the same here. So it is formed between the reaction. So if you were to add or to sum up this reaction, you find that this is on the left side, right? This is on the left side. I mean, this is on the right side. This is on the left side. So those will go. All right. We can have another hydrogen there. All right. So another hydrogen is there. So this one also, as you finish the reaction, it will cancel, right? Okay. So then we have other things. What else do we have? What else do we have? We have another chlorine there. All right, we have another chlorine there. We have another chlorine there. Okay, so you can see these ones are adding up what? 2. So we have another chlorine there. We have another chlorine there. Okay, so I'm just showing you what can happen as a result of this reaction. So as you add chlorine plus these 2 hydrogen, so this will get this chlorine and also this 2 hydrogen. So when we show that chlorine plus, I mean chlorine to chlorine bond plus hydrogen to hydrogen bond, there were some intermediate formed between the reaction. So what we have remained with is this one. All right, so we have remained with chlorine plus hydrogen, again this one, plus chlorine plus attached to hydrogen like that. All right, so you can see this plus this is just chlorine 2 plus hydrogen 2 like that. Then we are now having 2 things, so we'll say hydrogen chloride, which is just hydrochloric acid. So we are done here. So the series of steps that we have just formed here is what we call now reaction mechanism. So this is what we call reaction mechanism. So if you are asked to say what is a reaction mechanism, this is what we mean. All right, so from there, this I said this can be reaction intermediate. I mean this can be intermediate or transition state. So these two can be transition state or intermediate state. So it depends with what the stability. So the stability will actually what? Or actually matters. All right, so that is it. Let's see the energy diagram so that we can compare the stability of these guys. So that's about, I just wanted to show you that they'll be formed as the product turning into what? I mean the reactant turning into what? Into product. Okay, so the best energy example we can have is let's say we have energy diagram there. All right, okay, so let's say we have energy diagram there. Okay, so we have this side, we have okay, the energy diagram will go like that, then will come like that, then we'll drop down there to the what? To the what? To the product. So these are what we call now products. All right, these are what? Reactant. All right, okay, so now what here on this on this tip here, or on this just apex, we find what we call now a transition state. A transition state will be located here. All right, so that's for a transition what? State. Okay, then down here, all right, down here we find what we call now intermediate. All right, so this is the energy profile diagram. So you should just master it for both reaction, for both intermediate and the transition state. Then here we find the reaction coordinate. All right, so you write reaction coordinate in this column. then here it's what is the energy that we find here. Okay, so as the energy, you need to know that the diagram for energy, it does what, it increases as you go up. All right, so as you go up, energy increases. All right, so this is the what, the profile energy diagram that you can have for these guys, both intermediate and also transition state. So we can see now, we can even define from here. We can say a transition state, so you can say a transition state are just, this is just a theoretical structure which is too unstable to observe. All right, so it is too unstable to be observed because the energy, it has its maximum energy. So once something that has maximum energy, so by the way, these were supposed to be at the same rate, these ones, when you draw them. Okay, so these are what a theoretical structure. So these are theoretical structure. All right, so transition state, these are just a theoretical structure. Okay, so we are drawing the definition from that. That are two what, that are too unstable. So they are unstable. You can see something that has high energy. We talked about conformations. What causes conformation? Sometimes it's the unstableness of the what, of the molecule itself. So the forces that are between it cause it what, to be not to be stable. So something that has high energy is not stable because reactions are taking place frequently in that molecule. All right, so that are too unstable to what, to observe. So you can't observe them in that they are at the highest energy or peak of the what, energy diagram. So that's about what, transition state. So what about intermediate state? So this intermediate state, we can see now to say they are here, right? So we say intermediate state are stable enough to be isolated or detected. You can detect because the energy is low, but for these guys, they are able to react frequently because they have what, that maximum apex or just that peak energy. So we can say transition an intermediate state. All right, intermediate state are stable enough. So they are stable enough, they are stable enough to be what, to be isolated or detected. All right, so they are unstable, they are stable, these are stable. The first ones, they were unstable to even see them, but these guys, they are now stable to be isolated or detected. You can detect them because the energy is very low, and they can be at least in fact isolated under special cases, such as in low temperature. You can isolate them and put them aside. In a situation by want to see them, you can use what we call an instrument called spectroscopic to see them. But if you fail, you can conduct an experiment just to do what, to again to see them. Okay, so that's about intermediate state and also transition state. This is the general energy diagram. So we can isolate these guys under what special occasions, such as to store them in a low temperature or just in the matrix isolation. It's a situation whereby you put them together with other substances, then you isolate them. So that's what we call matrix isolation. Then so we can observe these guys through what we call now a fast spectral microscopic, or that instrument, spectroscopic. We can observe them through that instrument. I'm talking about intermediate now. All right, so we can observe that intermediate using this what, spectroscopic. All right, then the other thing that we can see is If we fail to see them, we can infer them through the experiment that we can conduct. All right, so in this thing there are principles that are used. All right, okay, so they are principles, so we are rubbing everything. Hope that is clear about the. So you can tell them to say they are both short-lived molecule. So for even defining transition state, you can say these are short-lived molecules, all right, that are which are theoretical structure to that are even too unstable to observe. All right, so put the way to say they are formed as the product turning into what, I mean reactant turning into what, products. So you explain like that. All right, so include that definition. But for these guys, for a transition state, they are unstable to do what, to observe. Then they are too unstable to observe. But for intermediates, they are stable enough to be isolated or detected. So we saw that they had the lowest energy what on their energy diagram profile. So that's about the transition state and also the intermediate state. So in this case again, you are going to find some principles used in this study. All right, especially for what's this, for intermediate and also transition state. Let me start with the principle called Hammond's postulate. All right, so Hammond Hammond postulate. All right, so this Hammond postulate state that the geometry, all right, the geometry and the shape of what, let's say the geometry is sp3d, everything like that, the geometry and the shape of what, of transition state can be inferred through the react, or using the product or the reactant through it, in which it is close to what, to energy. All right, so we can say that Hammond's postulate is talking about what, the transition state. Okay, so the transition state will be referred or inferred using the energy or the product or reactant that is close in energy. All right, so if we are able to tell the energy of this transition state, all right, so if we were able to see the energy of this transition state that we are working on, that energy we can refer it to that what, product or reactant of which to which they are what, similar in energy. Then we'll be able to do what, to give the shape and the geometry. Using that, it's more like a reference. All right, so the energy, the shape and the geometry of what, of a transition state. So I'll say transition state presented by S there. Transition state can be what, inferred either in the reactant or product to which is what, closer in energy. All right, so we can infer the shape and geometry of what transition state using the reactant or product of which they are closer in energy. That's about what Hammond's postulate. Another principle that we can find is what we call microscopic reversibility. All right, so pay attention to this, microscopic reversibility. All right, so we call it now microscopic So this one is just talking about all right, so microscopic reversibility is talking about now the intermediate state. So the intermediate, we said, something that is in between the reaction, I mean the reaction of which the reactant are turning into what product. So it's something which is in between. So the intermediate that will be there in forward reaction should be the one which will be present in what, in reverse reaction. So this under the same conditions, the intermediate, all right, present in what, forward reaction should be the intermediate, all right, intermediate in the reverse reaction, all right, so in the backward reaction, all right, like that, all right. So let's say the intermediate, as let's say A reacted into what, A plus B gives what, C, then the under the same condition, by the way. So the intermediate which was there, let's say, is D. So this D should be the one as C turning into what, into A and what, B. So in the what, reverse reaction, so the intermediate should be the same under what, under same conditions, all right. So those are the principles used, so expect them in an exam. Expect even the definition for intermediate, and also for what, for transition state. So expect the definitions. Let's talk about now intermediates in general. So intermediates are now what we call, we'll talk about intermediates more because they are bulk than what, than these transition state. So let's talk about intermediates. All right, so intermediates, we said those are short-lived molecules formed as reactant are turning into products. That's what we call intermediates. So we call them now reactive intermediates. All right, so they are there in the reaction. That's why we call them reactive intermediate. So they can be of main. So something that is of main, they are actually 3 in type. Okay, so reactive intermediate, all right. So they can ask you to say gives maybe just 3 example of reactive intermediate, all right. You should know them, all right. So the first one that we have is what we call now carbocation, all right. So carbocation, is just a situation whereby carbon is what, positively charged. We call it carbocation, all right. So the other intermediate that we can see, so carbocation will have, this is charged, let's say we have some groups there. Let me just put hydrogen there, hydrogen there, hydrogen there, all right. So the other group that we can give for reactive intermediate, we can also give what we call now a carbanion, all right, carbanion, all right, carbanion. So this one now is what, a situation whereby you can define that as carbanion is a species in which carbon is what, negatively charged. Once it's negative, then it gains some electrons. So that is it. I can put some hydrogen just in general, all right. And also they'll have some stability. So the other thing that we can talk of is so we can define carbocation as a species in which carbon bears a positive charge. Carbanion is a situation or a species in which carbon bears a what, a negative charge. Then we can have what we call now a radical. So a radical is a species in which carbon has what, equal electrons. So we will just leave it like that. Is that equal electrons, so we call it a radical. Is it undergo homolytic reaction or just cleavage? So let me put some hydrogen there, all right. So some hydrogen there. So this is what we call a radical. So the other guy we can talk of is what we call a carbene. All right, so these are just examples of what. So a carbene is a species in which carbon bears somewhat some. All right, all right. So the most important ones are these two. So we'll also we'll give the stability of these two because that's where the exam lies on. So we'll be talking about carbocation and also carbanion. So these carbocations or carbanions will be grouped as tertiary, primary, or secondary. All right. So the first general thing we can have is what we call now a methyl. All right. So a methyl there. All right. A methyl carbocation, so I'll talk about carbocation now. A methyl carbocation will look like this. Okay, so we have a methyl there, right? A methyl is the one whereby there are 3 hydrogen bonded. All right, that's what we call a methyl. So since it's a carbocation, we'll put it a positive like that. All right, good. Are we good? So this is what we call now a what? Because it's a carbocation, meaning it has what? It has lost some electrons. Okay, so the stability will matter. So we'll call it, we'll have, when carbon is bonded to other, let's say one carbon, this is what we call primary. All right, if carbon is bonded to 2 things, to 2 carbons or groups, we call it what? Secondary. All right, if carbon is what? Is bonded to other 3 carbons, we call it what? Tertiary. All right, quaternary, but will be just ending at tertiary. All right, so this is what we call primary, this is what we call now secondary, this is what we call now tertiary. All right, okay, so the stability now matters. How do we see the stability? Let's see the stability of these guys. Okay, so there will be a methyl as our what? Starting our basic carbocation. Then we can now start putting the groups of which carbon. Just that's the reason why if you are finding something to be tertiary or primary, secondary, you consider the number of carbon bonded to that thing. All right, even a group of alcohols, that's what we'll be doing. All right, so we are studying organic chemistry. So for carbocation stability, all right, so carbo stability. All right, so these are now reactive intermediate. All right, so what we do here is, I say the stability now, I'll give the reason why it is like that. All right, so it will go like third carbon or tertiary carbon is more stable than what? Secondary carbon. Again, the secondary carbon is more stable than what? Primary carbon. Again, this primary carbon is more stable than what? Just that methyl, which was our starting point. All right, so that's the stability of carbocation. Let me show you on your energy on the energy diagram, and I'll give the reason to why it is like that. Okay, so you give, let's say you put R where R is just number of carbon. I won't show the number of carbon to make it what? Tertiary. All right, so there must be 3 things bonded to that carbocation. All right, so we said this will be this is the third degree carbon. This carbon is 3rd degree. All right, that's why it's there. All right, then the other one carbon I can put here is what? All right, so I can put hydrogen there. I can put this R where R is just number of carbon. I can put wherever I put this R. All right, I have 2 now, so meaning is tertiary, so I have 2 R's, so I'll put that. Then less. Okay, less. What is the last thing? I'll put R there, then hydrogen there. All right, then again hydrogen there, then continuous positive charge. Then I'll put the methyl there. I'll just put the methyl. All right, so the methyl carbocation will look like this. All right, so this is the methyl carbocation, so they are stable. Why is it like this? We know that this guy is lacking some electrons, but when we bring these groups, R is a group, let's say a carbon, which is just a methyl, so this guy, it has also some other electrons. So and also this guy, this R here, or this carbon which can be here, it has also some electrons. Have you seen? So it has also some electrons as well. So this guy is lacking some, is lacking some electrons. So that's why it's positively charged there. So the chances of being or the chances of being given the some electrons by these groups which are just nearby is higher. All right, so it feels stable when it has some other groups, because it's lacking. It's more like you don't have brain, tawako atamano, then you stay with people, you feel that comforted, you feel like you are also what, intelligent, when you stay with people who are intelligent. That's the reason why this guy is less intelligent, but there are guys who are intelligent around it, so it feels comfortable, just like that. Just like girls, they feel what, they feel good when they know someone who is famous. So these guys are famous, then this girl is seated there between these guys. So that is it. That's the reason why carbocation stability increases, the number of groups what increases. All right, so that's about it. So we'll now talk about what? We'll now talk about the carbanions, which is the last thing. So we'll talk about the carbanion. Okay, so now the carbanion stability. Okay, so carbanion stability so we saw that the carbanion will be what, will be having a negative charge, like see, it has gained some electrons. So the general carbanion is what, is like this. So let me put some hydrogen there, some hydrogen there, some hydrogen there. So we can see there are two things, two electrons, and it is now negatively charged because of those two electrons that is acquired from just a certain bond we don't know. So this is a general carbanion. So a situation whereby a carbon bears a negative charge, we call it a what, carbanion. All right, hope that is clear. So now how do we see the stability? The stability now for this guy is opposite. Why? Electrons, guys, are very important as you are studying organic chemistry. So what we do is now the stability goes like this. All right, so I'll start with the third degree carbon for this guy. So the third degree carbon for this guy will look like this. All right, where these are just groups. It can be carbon or any other group. All right, so we said it has what, some free electrons, then it is negative because it has borrowed those electrons. All right, so this is what we call now third degree carbon. All right, then we have now the second degree carbon, of which it will look like this. I can put some R, which is the group, and also a group there. Then I can put the hydrogen there. Then this is having a what, a negative stew. So this is what we call now a tertiary, because there are two other groups. All right, then the other thing that we can talk of is I can now come to what, 1 degree. So I'll put R there, 1 degree. So then I put some hydrogen there. All right, so this is what, a negative charge, which is carbanion. Then the list now we can have is now a methyl carbanion. So a methyl carbanion will look like this. Okay, so it has what, some free electrons, then a negative charge because it has acquired those electrons. All right, so degree, then a methyl there. All right, so the stability now goes like this. This one is less stable than what, secondary, tertiary, and also just primary. So a methyl is now what, more stable. Why? We don't want other groups, these electrons, because if we bring, let's say we have this carbon there, which is what, which is the tertiary. Okay, it has what, some other groups there. All right, okay, let me say those are carbon. Again, it has some other groups which are just carbon, like that. Okay, so we don't want in a situation whereby this guy, okay, it is now negative, it has already some electrons, but again we bring other electrons, these guys who are rich. So meaning that there will be that repulsion, or you get the point, the compound will not be stable. All right, hence this is what, reducing the stability of what, a carbanion. Okay, so this guy feels what, feels nice when there are other just lacking things, so that he can distribute to these guys. Now they are all rich in this compound. The situation whereby you all have money, you start killing yourselves. That's how it happens. So when people have money, they will start killing so that just this one remains. So this happens also with these molecules. You get the point. So the stability will matter. So as you have a lot of groups, the stability what reduce, because electrons will be repulsing, repulsing. Then as you go now to less electrons, then at least it is now feeling that comfortable. As you go to at least, then finally this is now the highest, okay, more stable. So this is more stable. All right. For carbanion, then this one is more stable. For what? For carbocations. So that's about the stability, everything like that, and that's about it. It's important that you have understood these. Exams will be coming to say define carbocation, carbanion, give the stability, okay. So the next thing that we'll do is the reaction, okay. So that is it. Don't forget the energy diagram, profile diagram. That is very important. Also, don't forget how to label the energy diagram. Give these three carbocations and also reactive intermediate, of which we said we have radicals, carbanions, carbenes, carbocations. But carbocation and carbanion are the one which are major in our study. So exams will be coming just like that. Make sure that you do what you understand. Thank you very much for watching the video. Please subscribe. This is just a free lesson we have posted for you. Others people are paying for these lessons, but you are just what listening. So it's very important. It covers everything you want. We are covering exam standard. We are not just bringing these topics and also lessons. We actually aim exam question standard. So that is it. Thank you very much. See you in the next video, guys. Let's meet in the group. Let's meet in the group. I've muted everyone. No one can speak now. So let's meet in the group. Bye.